Today I'm going to talk about classical and deep learning approaches to studying longitudinal time series of brain imaging. I'll talk a little bit about why it's an important problem and a few different approaches that we've been developing to solve, or at least begin to address this problem. So a lot of my work focuses on Alzheimer's disease. The burden of Alzheimer's disease is very large and is increasing as our population lives longer and as our baby boom generation begins to age. And you can see in this graph here how many people are projected to develop dementia by 2050, and it's quite large. So this is an important problem to address in our society. Unfortunately, Alzheimer's disease can't actually be diagnosed in living people. Alzheimer's disease in living people is only diagnosed as probable Alzheimer's disease, and there's various ideas about how you can change that diagnosis to high probability or low probability. So a few years ago, there was an article in the New York Times talking about this idea, and they said in 382 patients whose doctors gave them a diagnosis of dementia before death, the autopsies showed that Alzheimer's was not the cause in 89 of them. Yet 58 of those 89 patients, or 65%, had been incorrectly told that they had Alzheimer's disease. So it's still a challenge to diagnose this disease in living people. Some of you have probably heard over the past few years there have been a few new drugs developed for not curing Alzheimer's disease, but slowing the degeneration due to Alzheimer's disease. So now it's becoming critically important to figure out who actually has Alzheimer's disease rather than some other process which is causing symptoms of dementia, so that potentially those people get treated. Now, the way Alzheimer's disease is actually diagnosed at autopsy is by cutting out pieces of their brain and looking for two different compounds. And this image on the top over here, can you see my mouse? Yes. This image on the top is a piece of brain tissue in the medial temporal lobe, where I'm pointing here, stained for amyloid beta plaques. And you can see a few little brown spots scattered around this part of the brain. The other object that people are looking for to actually diagnose this disease are called tau tangles. Now, amyloid plaques are extracellular, and tau tangles are intracellular. These are actually dead neurons. And you can see they start accumulating around the brain in the medial temporal lobe as well. You can see them in this dark brown color over here. Now, over the past few years, people have been doing a lot of work to understand this family of biomarkers that can be used to actually diagnose or stage Alzheimer's disease in living people. Even though for now it's currently only used for research purposes, the framework is really beginning to solidify into three categories. What's called the ATN framework has been developed, where A stands for amyloid, which are those big brown blobs that are extracellular that I mentioned. T stands for tau, and the tau are the smaller brown dead neurons. And the N stands for neurodegeneration. Neurodegeneration is something we can measure from MRI images, and it just means how much your brain is atrophying or shrinking or growing according to certain patterns. Currently, neurodegeneration as a biomarker is considered not specific enough to really be used to diagnose Alzheimer's disease, because there's a lot of different diseases that can cause neurodegeneration. And one of the focuses of my work is to try to improve these neuroimaging biomarkers by leveraging time series of imaging data as opposed to just single images. Now, this figure here shows a particular example of the trajectory that Alzheimer's disease follows. And on the y-axis, we see different biomarkers of the disease as they progress from normal at the bottom to abnormal at the top. And on the x-axis, we see the different stages of the disease. So on the left-hand side, you begin cognitively normal, no symptoms. As the disease starts to progress, you develop mild cognitive impairment, which is a phase where generally people have mechanisms for compensating for the changes that are going on in their brain, and they may not notice that anything is actually going wrong, but certain clinical tests can actually examine for this. And finally, in the later phase, you progress to dementia, where the cognitive changes are actually negatively impacting your life, and the disease is ultimately fatal. Now, the order that these biomarkers appear is important. On the left-hand side, we see a curve that originally the accumulation of A beta begins. This is sort of the first change we can observe in people. Then a few years later, still before any symptoms appear, tau tangles start accumulating. And there's a few different ways we can measure these through PET scans, for example. A little bit later, we start to be able to observe neurodegeneration changes in MRI images, so a pattern of atrophy in brain images. And then finally, symptoms that can be interrogated through psychiatric evaluations start progressing from normal to abnormal. So the goal of my work here is essentially to try to shift this orange curve to the left as much as possible, because data for this orange curve can be collected completely non-invasively through MR imaging. Now, these two biomarkers, amyloid and tau, have very different characteristics, even though they both proceed from abnormal to normal. Amyloid, in particular, through autopsy studies in the 90s, was determined by Brack and Brack, a husband and wife team of neuropathologists. The distribution pattern and packing density of amyloid deposits turned out to be of limited significance for differentiation of neuropathological stages. Essentially what that means is amyloid can appear anywhere in your brain at any time. It moves from normal to abnormal, but there isn't really a characteristic trajectory that we can use to identify the disease. On the other hand, they describe tau as follows. Neurofibrillary tangles and neuropil threads, in contrast, exhibited a characteristic distribution pattern. The first two stages were characterized by an either mild or severe alteration of the transentorhinal layer pre-alpha. So this on the right-hand side is a picture of the medial temporal lobe that they drew, Heiko and Eva Brack. And these little dots here correspond to the dots that I showed on a previous figure. So these tau tangles are progressing according to a very stereotypical pattern. And in fact, other research has shown that neurodegeneration parallels this distribution of tau tangles. So if we look for a pattern of neurodegeneration over time that parallels the known changes in tau tangles over time, then we can conclude that this pattern of neurodegeneration is specific for Alzheimer's disease. Now, there's still some challenges as to how we could apply this in practice. Most of the evidence has come from very high resolution, very high quality, homogeneous research-grade MRI scanners. If you actually look in clinical populations, image quality is much worse, the samples are heterogeneous, the resolution is not as good. So can we actually build a technique to quantify these patterns of neurodegeneration over time using real imaging data? A related question is, once we identify these trends, are we going to be able to predict what your brain might look like in the future, given the disease trajectory that you are on? If we can address these issues, we'll have the ability to shift this orange curve, this neurodegeneration curve, over to the left, meaning we'll be able to diagnose the disease, hopefully, from a time series of clinical images that you may have acquired for other reasons long before symptoms of the disease appear. So to address this, I'm going to focus on three different areas today. How can we actually quantify neurodegeneration over time? So what does it mean that we have a spatial pattern of atrophy in the brain? How can we assign numbers to that idea? Second idea is, how can we model this variability in pixel values in heterogeneous data that's coming from real clinical populations? And finally, we're going to look at techniques for combining these features into a deep generative model to actually be able to predict what your brain might look like in the future, depending on your age, an amount of elapsed time, and what diagnosis you might have. So let me start at the beginning. How do we actually make quantitative statements about neurodegeneration? Traditionally, it's been quantified using three steps. First, we define a typical brain, which is often called an atlas. Next, we define individual differences. So how is your brain different from the typical brain? By using coordinate maps. So these are functions that say, how is this part of your brain different from the typical brain? You know, in a typical brain, the amygdala is over here, but in your brain, the amygdala is over there. And finally, we can look at these maps to identify patterns of atrophy. A common approach is to use the determinative Jacobian of these maps. The determinative Jacobian tells you about volume changes. So we can quantify in what areas is the volume of your brain tissue increasing, and in what areas is the volume of your brain tissue decreasing. So let me address each of these steps. So first of all, what is a brain atlas? Well, the first real approach towards developing a brain atlas happened more than 100 years ago by Corbinian Brodmann. He examined through a microscope the cellular structure in the cerebral cortex, the surface of your brain. Some of his drawings are shown here on the left. And by noticing different patterns in how the cells were arranged in your cortex, he was able to reproducibly divide your cortex into 52 different areas. And these areas are still used today. They're called Brodmann areas. At the time, he hypothesized that each of these areas had a different function. And today, we now know that to be true, but at the time, it was a relatively new idea. Today, modern brain atlases differ from what Brodmann developed 100 years ago. These are now dense three-dimensional images, so grids of voxels. People typically identify about 300 different structures in the brain, which you can see here represented in different colors, and these are represented as 300 different binary masks. And these atlases cover the cortex. Here I'm tracing the cortex, which Brodmann studied, as well as the deeper gray matter and white matter structures in the brain. Now, to really take this idea to the next level and start making quantitative statements, someone named Taylorak added a standard coordinate system. And you can see the coordinate grid associated with Taylorak space that he drew. His goal was to figure out how we should cut into the brain in order to treat epilepsy. And by building up this coordinate system, which he added on top of the brain atlas, he can now communicate to different surgeons at different hospitals exactly where to cut. So how could a different surgeon cut your brain in the same place? Well, you give them a list of XYZ coordinates, and they refer to this coordinate map, which is attached to our standard brain atlas. Now, based on these coordinate maps, we can start describing individual differences. So how is your brain different from a standard brain? These individual differences are described by a coordinate transform, which we often call a function phi, the Greek letter phi over here. So we take a position x in the typical atlas brain, and we say, where is that anatomical structure located in your brain? So let's see an example of what that might look like. Circled in blue here is the hippocampus, and in this atlas image on the left, you can see it has coordinates 25, -35. On the right-hand side is a new image. Maybe this is your brain. Once again, we can circle the hippocampus over here in blue, and notice that it's located at the point 30, -15. So we know some sort of constraint onto this phi function. If we input the value 25, -35, we need it to output the value 30, -15. Now all we have to do in principle is repeat this for every single anatomical structure in the brain, and we end up getting a displacement field. And we can represent that displacement field as a deformed grid that you can see here in red. You notice that some of these grid cells are larger and some of these grid cells are smaller. The grid cells that are larger are regions where your brain is bigger than the standard brain. And in this person, the larger regions are around the ventricles. So these are fluid-filled spaces which start to grow as your brain tissue begins to degenerate. So we can now start to make quantitative descriptions of atrophy patterns and neurodegeneration patterns using these phi functions. To make that a little bit more precise, here's an example over here. On the bottom, I'm showing a two-dimensional contour of a structure in your brain called the hippocampus. Hippocampus is very important for learning and memory. It starts to degenerate in Alzheimer's disease fairly early on. So in cyan, we see the atlas brain, the typical brain. In red, we see the hippocampus of your brain. We estimate a phi function, which is shown as this transformed grid, which will deform the shape of the cyan atlas to match the red hippocampus in your brain. Once we do that, we can look at the change in area of each of those grid cells, and that area change is shown over here on the right-hand side in different colors. Red means atrophy. Your brain is smaller than the standard brain, and blue means growth. Your brain is bigger than the standard brain. So we could just take the value of atrophy in all these grid cells, stick them into a vector, and we now have a representation of neurodegeneration in your brain. So how do we actually compute these phi functions? There's some properties that we want this phi function to have. In particular, in order to calculate the determinant of Jacobian, these local volume changes, we want to make sure that this function is differentiable and invertible. So to build a phi function like this, we can go all the way back in time to the 1700s when Leonhard Euler, studying fluid dynamics, built a framework for creating these displacement fields, phi, as a function of velocity fields. And as long as the fluid flow, the velocity field, was smooth, we can guarantee that these phi functions will always have the property that we want. They're an object that we can always compute the determinant of Jacobian of. They're always going to be smooth and always invertible. So we can pose this as an algorithm. This is a problem in optimal control. As an input, we have an atlas image, so this is the typical brain, and an observed image. This is your brain. We want to figure out how your brain is different from the typical brain. And we define a reproducing kernel Hilbert space of smooth velocity fields. So that essentially says we want to identify a smooth coordinate transformation over here so that it will be differentiable. We can use its determinant of Jacobian. And this kernel, we just want to decide how smooth is relevant. So in the brain, we'll use a kernel here on the scale of 1 millimeter or so, and that will be sufficient to make sure that we have invertible transformations that are accurate on the scale of 1 millimeter. So we just want to minimize this objective function, or SSE is sum of square error, to make the transformed atlas as close as possible to your brain. And then we can study this phi function to understand neurodegeneration patterns in your brain. So a little bit more visualization of Euler's approach to using flows to construct phi functions. Suppose on the left-hand side in cyan, we have a template hippocampus, the same structure I mentioned before that starts to degenerate in Alzheimer's disease. And on the right-hand side, we have your hippocampus, which is called the target. So we can build a flow to describe these neurodegeneration patterns by first laying down a time axis here. And the units are arbitrary, so we can just scale it between 0 and 1 if we want. We then start laying down smooth velocity fields. So these are little arrows at every point in space. Here at time 0, at time 0.3, 0.7, and time 1. Then we just need to integrate these velocity fields over time. Displacement is the integral of velocity over time. So we can start generating these phi functions. Once the functions are generated, we can apply them to this ideal brain to slowly morph its shape until it matches the shape of your brain. So this problem was originally solved in 2005 computationally. And since then, we've been looking for newer and harder applications of this problem. Now, the fact that time appears in Euler's formulation of this problem kind of is a clue that we might be able to use this formulation to describe how images change over time, rather than just a pair of images. And solutions to this problem actually have a very interesting property. I mentioned we want to minimize a kinetic energy plus an accuracy. So this kinetic energy is like a regularization term, which is just going to say we want the velocity fields to be smooth and small. So in fact, any solution which minimizes a kinetic energy is called a constant speed geodesic. Any constant speed geodesic exhibits a conservation of momentum law, so that we can actually compute any velocity as a function of time as an explicit function of velocity at time 0. And over here is an equation for how we do that computation. The details are not that important, but on the right side we usually use the symbol exp to denote these geodesic straight lines in the space of fluid flows. And this is called the Riemannian exponential. So by solving this brain mapping problem to identify a phi function, we also identified what it means to be a straight line in the space of neurodegeneration. And we can use these straight lines to start doing linear regression, or what's actually called Riemannian regression in this sense, and study how the brain changes over time with many different images. Now here's just an example of what that looks like. As I just mentioned, these geodesics are straight lines in the manifold of brain shapes. And by straight lines, that means they're the shortest path between two different points. We define this object called the Riemannian exponential, which takes your velocity at time 0 and shoots it out along a straight line to give a phi function, so a pattern of neurodegeneration, as a function of time. So I just wanted to walk through the relationship between linear regression and geodesic regression. So over here on the bottom left, we imagine time on the x-axis, and on the y-axis is some variable that's going to describe the shape of your brain, the neurodegeneration pattern. And you can see there's some data points changing over time here, and the objective of linear regression is to fit a straight line through these data points. So let's do that. We need to know two things. We need to know the intercept, so essentially a vector that points from the origin to the center of our data, and we need to know a slope, so another vector that points tangent to our data. Once we have these two ideas, we can construct a straight line through our data, look at the sum of square error, and minimize the sum of square error over these two parameters. Now, if we want to extend this to this idea of geodesic regression using straight lines that are defined by this Riemannian exponential, we're going to optimize over two similar parameters. So the first thing we want to optimize over is not an initial position, but an initial velocity. We can then trace that initial velocity forward to the center of the population using the Riemannian exponential. The second thing we need is a tangent vector to this curve that we can then again trace out as a straight line. It looks like a curved line here, but this is in fact a straight line on the manifold of brain shapes. We can trace out this curve, which has a tangent vector given by v1. So the two optimization problems are closely related. Once we have this parameterization, we can look at the sum of square error and minimize it to find these two parameters, v0 and v1, that will describe a time series of brain images. So we can write this problem, again, extend the original brain mapping problem to a population of images. So we'll now sum over from I equals 1 to n images. We have two initial velocities here. My apologies, there's an error. Please ignore the I and the C. We'll come to that later. And we just solve the same problem. We construct one trajectory from the origin to the center of the population, another trajectory that patches through the population, and we want to make this transformed atlas brain as similar as possible to your brain at the time ti. So this is a closely related problem, and we solve it using gradient-based methods. So I just wanted to show a couple of examples where we've applied this algorithm before. In one example, we studied a moving heart, and this is actually a mouse's heart, so it's very small. It was imaged with a certain type of modality called tagged MRI, and the tagging kind of killed the signal along a particular grid. And by observing how this grid changes over time in the MRI image, we can see how the heart is twisting and deforming in a way that we couldn't with a regular type of MRI. So that's one example where we've applied this method to time series of imaging data. And by making only minor modifications, we can do things like super resolution. So as this object is changing over time, we're actually sampling the same anatomy many times at each pixel. So even though it seems like a harder problem, the fact that this object is moving, the fact that it's moving actually makes it an easier problem. We have multiple observations. We just have to estimate how they're moving. Another example we looked at that's related to Alzheimer's disease is we looked at contours of the entorhinal and transentorhinal cortex, a little piece of tissue, which is the first thing that starts accumulating tau tangles in Alzheimer's disease. And in the top row here, we have 4 different observations of this little piece of cortex from the same person. And you can see these observations are quite noisy. Some are big and some are small. So in order to study the pattern of neurodegeneration over time, we'd like to fit this smooth trajectory using the Riemannian exponential that passes as close as possible through these observed time points, but at the same time filters out sources of noise and other errors. And on the second row here, you can see what this smooth trajectory looks like that we estimated. Using this smooth trajectory, as a function of time, we have this phi displacement field that can be used to precisely quantify neurodegeneration. All right, so this sort of gives us an idealization of how we can study shape in the human brain and make quantitative statements about it. But how do we actually deal with the heterogeneity of clinical images? We have different scanners. Pixel intensities are not calibrated. There's different MRI pulse sequences. Resolution is inconsistent. Sometimes we have high resolution in one dimension and low resolution in another dimension. So our approach to solving this problem is to treat it as a dictionary learning problem. We want to say you observe a bunch of images over time, that's I, and we'd like to be able to model the intensity of the pixels in these images over time as some linear combination of dictionary elements. So I over here are the dictionary elements, and C are the linear combination coefficients. So at time ji, for I equals 1, you might have gotten a T2 MRI scan, and for I equals 2, you may have gotten a diffusion-weighted MRI scan, and each of those will have a different contrast, but we can model that contrast as a linear combination of the same set of features. For example, where is the gray matter in your brain? Where is the white matter in your brain? Where is the skull? Those could be elements of our dictionary that model all possible different contrasts that you might observe in a heterogeneous population. So we now have a joint optimization problem where this phi over here is our phi function, which depends on time in the way that I just described, and we have to estimate this dictionary of image contrasts I, and we have to estimate this set of linear combination coefficients C. So this is a hard problem, and it's actually non-identifiable, you can probably see, because you can multiply C by 2 and divide I by 2, and you get exactly the same answer. So we introduce a couple of constraints here. We'll say that the columns of the dictionary are orthogonal, and the linear combination coefficients are orthonormal. And then we can get a unique solution, and I'll justify why those constraints are a good idea in a minute. So how do we actually solve this problem? Well, we'll use an iterative optimization algorithm. First, we'll estimate some velocity field, then we'll update our dictionary, then we'll estimate the velocity field again, then update our dictionary again. So we already know in principle how to estimate these velocity fields, so how can we update this dictionary of different types of image contrasts? Let me write down this objective function here, which we'd like to minimize over C and I for a fixed V. So this just says we look for the contrast of the image at time I. and we take a linear combination, and we want it to be as close as possible to the image that you actually observed at this time. So what we can do here is change variables in the integrals over there, and this determinative Jacobian factor shows up, and I colored it in pink. And then we could start treating this as a matrix problem by discretizing it over pixels. So let's say we have n patients, m atlas features, and v voxels. We'll start substituting some of these quantities with matrices. So let's let these linear combination coefficients be a matrix A. We'll let the voxels in our dictionary, our atlas image dictionary, be called X. And we'll let this observed data, J, transformed with this phi function, be called Y. And we'll let these Jacobian factors be called W. So we can write this down as a matrix factorization problem. You say we're looking for AX minus Y. We want to find A in X that minimizes weighted sum of square error. So this is a very well-studied problem. This is just a low-rank matrix approximation problem, which can be solved quite efficiently. The solution to this problem, when the weights are constant and equal to 1, is simply an SVD. We take an singular value decomposition of our data, we choose the first few singular vectors, and we've computed this matrix factorization. So the dictionary elements that represent different contrasts in clinical images, and the linear combinations of those elements that to describe how your different MRI scans looked at each time. Now, the SVD has been around for a very long time, but actually the weighted SVD was only solved relatively recently, about 20 years ago. It was solved in research looking to win the Netflix prize to do recommendations. So if I like this film, would I like that film? And there's an interesting paper about how the weighted SVD arises as a solution, which we've exploited for our problem. Now, the idea of the algorithm is you take a current guess of your factorization, and then you replace your data with a linear combination of your current low-rank approximation and your actual data, where the weights in this convex combination are given by these Jacobian factors. So we can solve this problem using the singular value decomposition relatively efficiently. Now, these weights as determinant of Jacobian factors, they hold in the case where we're looking at continuous functions. But once we actually discretize everything at multiple resolutions, we have another way of formulating W, which is not exactly a determinant of Jacobian here. It's the adjoint of our discrete interpolation method. So that's essentially the transpose of the derivative, and I won't get into the details here. But there's an extension of this method to deal with discretization at multiple resolutions by only adapting the weights and leaving the other features intact. So with this in mind, we can look at a couple different examples of results. We applied this method to studying digital pathology images as part of a challenge called the Automatic Non-Rigid Histological Image Registration Challenge. And you can see here on the top, we have 5 different histology images. And using this method, we were able to jointly align them all, estimate elements of a dictionary, which you see on the left-hand side, and linear combinations of those dictionary elements, which you see on the right-hand side, to match the multiple different contrasts we see in these different histology images. So that's one example. And another example will come to the problem that I'm actually interested in solving. So here we observed 6 images over time of the same patient from the Alzheimer's Disease Neuroimaging Initiative. And what you can see here is that in some of the images, the face is present. In other images, the face is cut off. But we can solve this same problem. We can estimate a dictionary to represent any contrast differences over time. We can estimate these phi functions that describes how the shape of the brain is changing over time. We can combine all of the images into a dictionary, which is illustrated at the bottom left. And we can look at these determinant of Jacobian factors, which you can see as red and blue colors on the right-hand side here. And what you see is around the lateral around the ventricles, the fluid-filled spaces, we see a lot of blue. And that means that the brain tissue is degenerating, and the fluid-filled spaces are growing because your skull is staying the same size. And we also see an interesting pattern around the medial temporal lobe, where some areas are red and some areas are blue. And the idea is we can use this method to take heterogeneous images and produce a high-quality image and a map of neurodegeneration everywhere in your brain that can be used for diagnosis or disease monitoring applications. So in my last few minutes, I wanted to move on to a more modern approach. So if you've been following me, there's a lot of math and a lot of work went into modeling a complicated set of data. How can we study the brain? What does it mean to quantify shape? How can we look at pixels, et cetera, et cetera, et cetera? A more modern approach would just be to take all the data and stick it into a deep learning model and see what the deep learning model does. So we've done this as well as a complementary approach. We created a conditional variational autoencoder to generate samples of future MRI images conditioned on a past MRI, as well as demographics and disease status. So as an example of what this might look like, we'll input into our system a prior image of a person at age 65. We'll feed them into our conditional variational autoencoder, which I drew as a box here. But it's a white-colored box because my personal feeling is that variational autoencoders are a little bit more interpretable than some other deep learning models. And then we'd like to say, what will your brain look like in 4 years? If you're healthy, it'll look like this. Or if you have Alzheimer's disease, you can see the ventricles have grown in 4 years as the brain degenerates. So this is work that myself and my student Rose recently got accepted at the Mackay Conference for Longitudinal Disease Tracking and Modeling with Medical Images and Data. I'll tell you a little bit of the details of how we do this. So first, we developed a new type of conditional variational autoencoder that can condition on both images and tabular demographic data. So what's sketched here is sort of a traditional autoencoder. You take an image on the left-hand side, you apply a bunch of convolutions, and you downsample it to a latent space vector here. And in a variational autoencoder, we want to make sure that the distribution of samples in the latent space follows a known distribution. Usually, it's going to be, here we have a 10-dimensional multivariate standard normal, so 10 independent random variables. And that branch is called the encoder. And then on the right-hand side, we have a decoder. So we sample from the latent space, apply transposed convolutions to generate images, and we want to make sure that our generated images are similar to the images we input in code. Now, what we did in this work, because it's generally known that variational autoencoders don't produce images that are as realistic as other methods in generative AI, such as GANs, generative adversarial networks, or diffusion models. So we wanted to make sure we could condition on something and use that conditional information to generate more realistic samples and also solve an easier problem. And we had a talk earlier today showing how conditioning on certain things can simplify problems in some cases. So we expanded this into an architecture that we call the double encoder conditional variational autoencoder architecture. And what we did is we sort of introduced an asymmetry to this problem. On the left-hand side in our encoder, we're going to input 2 images, a baseline image and a future image. On the right-hand side, our decoder also will take this baseline image as an input. So instead of just it being a standard transposed convolutional neural network, the decoder actually becomes a U-net. So the symmetry is sort of broken here, but the idea of a conditional variational autoencoder still holds. Now, we trained this model on all of the MP-RAGE, so T1 structural MRI images from the Alzheimer's Disease Neuroimaging Initiative. We looked at all the pairs of images of the same subject over time. That gave us about 15 1,000 pairs from 907 different subjects. And we looked at the mean square error to evaluate how accurate our model was performing as compared to a few different alternatives as a baseline. So on the left-hand side in blue is how well our model performed on a held-out portion of the ADNI data. And you can see that the sum of square error is much less than any of the alternatives we looked at. The alternatives we looked at were a linear model based on singular value decomposition and using a traditional autoencoder and doing a regression in the latent space. So you can see this approach here does much better in terms of sum of square error. Now the orange curves here show us what the sum of square error was on an independent test set, so another longitudinal data set of images. And you can see our model still performs the best, but it actually has long tails. So this idea of distribution shifts and generalization that a lot of people have been talking about this week is important in this example as well. So here's a few examples of what the output of our network look like. On the left-hand side here is a baseline image. And as we move to the right, these are images that we predict. Now the top row shows the ground truth, the actual image later. The middle row shows a linear model, an SVD, and the bottom row shows our double encoder CVAE. And what you can see is that the linear model actually does a reasonably good job of predicting images in the case where the people are healthy and their brain is not changing too much over time. And what that means is the conditional variables we added are actually very, very helpful for making this an easier problem. But for someone with Alzheimer's disease, as you see on the right, the linear model is not identifying the neurodegeneration patterns appropriately, whereas our CVAE model does. And in this case, we predicted after 48 months with high accuracy how this person's brain would change over time. Now, what's really nice about the VAE framework, and I said that it's a little bit more interpretable than other deep learning models, is because the latent space has a known distribution, we can actually use it to build likelihood ratio classifiers. So instead of feeding in, instead of predicting a new image in the future, if we already had two images, we could just stick them both into our encoder and figure out where in the latent space that's represented under the hypothesis that a person has Alzheimer's disease or under the hypothesis that a person is cognitively unimpaired. And so we were able to do that to classify these pairs of images by sort of turning the generative model upside down and understanding something about the likelihood of the different conditional variables. Okay, so let me just summarize quickly. I'm right out of time. Neurodegeneration patterns are a potential biomarker for Alzheimer's disease, but challenges remain on actually using them in a way which is specific to Alzheimer's disease and will work with real clinical images. So to address this, we designed a system that inputs a heterogeneous set of clinical images and outputs one high-quality average MRI image as well as a map of neurodegeneration, where we're quantifying neurodegeneration using these phi functions, these displacement fields that tell you how your brain is different from some standard brain. Moving forward, these personalized neurodegeneration maps can be used to analyze brain images, diagnose people with Alzheimer's or other neurodegenerative diseases, and monitor the disease as people start taking new drugs that might treat Alzheimer's disease. Last, we tackled the problem of trying to predict images in the future by designing a deep conditional variational autoencoder to estimate future brain anatomy and turn this representation upside down to actually classify time series of imaging data using the same model. So let me just acknowledge funding sources from the Karen Toffler Charitable Trust, a few grants as part of the BRAIN Initiative, some studying Alzheimer's disease and some studying microscopy and MRI data. I wanted to acknowledge the people in my lab who have contributed. Bryson and Suchi are here today. Thanks for coming. Suchi in particular is working on these dictionary learning problems, and Rose He is working on these deep learning problems. So thanks so much for your attention and for sticking around to the very end of a long day.